Hello everyone, and welcome back to the Fluctus Channel. This massive armored bridge system was built to keep U.S. ground forces moving when the battlefield is ripped open by trenches, craters, riverbanks, and anti-tank obstacles. The Joint Assault Bridge, better known as the JAB, exists for one reason: momentum. In armored warfare, speed is not just convenience. It is survival. If Abrams tanks reach a gap and stop, the attack compresses, vehicles pile up, artillery finds the choke point, and the entire assault begins to lose tempo. That is why the U.S. Army needed a bridge layer that could move with frontline armor instead of arriving later as a vulnerable engineering afterthought. The result was a heavily protected bridge launcher built directly on the M1 Abrams chassis, using the heavy M1 suspension so it could keep pace with the same formations it was meant to support. That chassis choice is one of the most important facts about the vehicle. The JAB is not a truck with a bridge strapped to it. It inherits the Abrams family's mobility, protection, turbine power, and battlefield survivability, allowing it to reach speeds and cross-country performance comparable to Abrams formations. Official Army material says the JAB provides a military load classification of 115 normal and 124 caution, can span more than 18 meters, and has maneuverability comparable to the M1 Abrams and the assault breacher vehicle. That means this machine is designed to launch a bridge strong enough for some of the heaviest combat vehicles in the American inventory, while still fighting its way to the obstacle under armor. In training, the transformer-like nature of the vehicle becomes obvious. What looks at first like a bulky armored engineer platform suddenly lifts its launcher, unfolds the scissor bridge, and turns a dead stop into a usable route in minutes. Army and industry descriptions place bridge deployment at roughly 3 minutes for an 18.3 meter or 60-foot gap. That number matters because battlefield bridging is measured in exposure time. Every extra minute at the edge of an obstacle is another minute for enemy gunners, drones, or observers to react. The bridge, therefore, is not just an engineering tool. It is a stopwatch-driven survival system for armored columns. The bridge itself also deserves attention. Girder-style assault bridging is all about carrying heavy loads across a short but tactically decisive break in the ground. The span has to be strong enough for Abrams-class traffic, compact enough to ride on a tracked hull, and stable enough to survive the violent handoff from launcher to obstacle. Once in place, the bridge looks almost simple. But behind that quick action is an intense mix of hydraulics, geometry, weight distribution, and crew drills. If the approach angle is wrong, if the launcher is misaligned, or if the ground around the gap is unstable, a crossing can be delayed at exactly the worst moment. That is why JAB crews train so hard. They are not just learning to drive and push controls. They are learning how to assess a gap under pressure. Stop on the right line, launch with precision, recover the bridge, and move again before the rest of the armored force bunches behind them. This is what makes the Joint Assault Bridge such an interesting machine. It turns a 60-ton class tank chassis into a battlefield bridge in roughly the time it takes a stalled assault to become a target. And once that bridge drops, every vehicle behind it can keep moving, which is often the difference between an advance that breaks through and one that grinds to a halt under fire in a modern war. But dry gap bridging is only one part of the story. Once armored forces reach a river, canal, or flooded obstacle, the engineering problem changes completely. Instead of one launcher dropping one span, military bridge units begin assembling static floating modules into rafts or full roadway systems. This is where the improved ribbon bridge enters the picture. Official Army and engineering sources describe the improved ribbon bridge, or IRB, as a wet gap crossing system that can function either as a floating bridge or as a multi-bay raft, and it has supported Army and Marine Corps operations since 2003. In other words, when the gap becomes water, the U.S. military shifts from a transformer-like assault bridge to a modular waterborne crossing network. The modules themselves are only part of that system. Bridge erection boats provide the muscle and steering needed to move heavy bridge bays in current, align them, hold them in place, and help crews build a crossing under pressure. Army acquisition material says the BEB, the IRB, and their transporter are required to construct and retrieve up to 210 meters, nearly 690 feet, of floating bridge. That statistic reveals the scale involved. Engineers are not dropping a single portable bridge. They are effectively building a temporary floating road long enough to move an armored force across a river and then pulling the entire road back out again. The load ratings are equally revealing. Army sources list the IRB at military load class 96 for wheeled vehicles in normal conditions and 110 in caution conditions. While track traffic is rated at MLC 70 normal and 85 caution. Those figures explain why the system matters so much. It is not intended for light pickups or utility trailers. It is designed to move combat vehicles, troops, and supplies across water when permanent bridges do not exist or cannot be trusted. Once the bays are locked together and the ramps are seated, the water obstacle stops being a barrier and starts behaving like a temporary highway. That is the dramatic moment seen during tank river crossings. A heavy vehicle noses onto a floating span that should not logically be carrying that much weight. Yet the engineering works because every module, boat crew, anchor, and connection point is doing exactly what it was designed to do. The jab forces open the dry gap. The ribbon bridge conquers the wet gap. And together, they show the same battlefield truth. Mobility is not just about horsepower. It is about engineers creating a path where none existed before. River crossings also demand traffic discipline. Entry ramps must be aligned for tracked vehicles weighing tens of tons. Shorelines have to be checked for collapse, and launch sequence matters because one misplaced bay can slow the whole build. Boat crews, deck crews, and drivers all become part of one moving construction team. When that teamwork works, a formation that would otherwise sit exposed on the bank can begin crossing rather than waiting for a permanent bridge that may never come. But even the best crossing system fails if the armored vehicles using it cannot be recovered when something goes wrong. That is why the final part of the story belongs to recovery and breaching vehicles, built around the same heavy logic as the jab. At the center of recovery operations is the M88A-2 Hercules, a fully tracked armored recovery vehicle designed to hoist, winch, and tow vehicles as heavy as the Abrams family. BAE Systems states that the M88A-2 carries a 35-ton boom, a 140,000-pound constant pull main winch with 280 feet of cable, and enough power to recover mired, disabled, or damaged vehicles from ground, where ordinary wreckers would be useless. Those are not garage shop numbers. They are battlefield recovery numbers. The importance of that capability becomes obvious during M1 recovery drills. A main battle tank can weigh well over 70 tons in combat configuration. And once that much steel is stuck in mud, frozen ground, or broken terrain, the challenge is not simply pulling it free. Recovery crews must rig cables safely, position the recovery vehicle on stable ground, manage enormous loads under tension, and do it fast enough that the disabled tank does not block the route or become a liability to the rest of the formation. In rough weather or cold environments, the job becomes even harder. Metal stiffens, traction worsens, visibility drops, and every minute of delay expands the danger area around the stranded vehicle. This is where the Abrams chassis shows its versatility once again. The same family that underpins the Joint Assault Bridge also supports the M1 assault breacher vehicle, another specialized combat engineer platform built for one of the nastiest jobs on the battlefield. Opening a safe lane through minefields and obstacles. The breacher replaces the standard tank turret with engineering equipment such as mine plows and line charge systems. One of the most dramatic is the MICLIC, the Mine Clearing Line Charge, which can blast an explosive path roughly 100 meters long through a minefield. In practical terms, that means a vehicle based on the Abrams hull can fire a rocket-towed explosive hose across a danger area and detonate a cleared lane wide enough for following forces to begin moving through. But that kind of work happens close to the obstacle, under pressure, and often in the same ugly ground where bridge layers and tanks are already operating. So when an M1 throws a track, bogs down, or is damaged during breaching, recovery becomes part of the same larger engineering chain. In training, Abrams tanks and recovery units may have to help extract a disabled breacher, reconnecting the whole system of mobility, counter-mobility, and survivability. The bridge vehicle opens the gap. The ribbon bridge opens the river. The breacher opens the minefield. And the recovery vehicle rescues the machines that make all of that possible. Seen together, these statistics tell the deeper story. A 60-foot assault bridge launched in about 3 minutes. A floating bridge system that can build or retrieve nearly 690 feet of roadway. A recovery vehicle with a 140,000-pound winch. A breacher that can clear roughly 100 meters of mined ground in one violent blast. None of these numbers exist in isolation. They are all measurements of battlefield momentum built by a nation determined to win on all fronts and under all conditions. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.